I'm Professor Gustavo Rehder from University of Sao Paulo. I'm presenting a paper, Suspended CPW Integration and Nanoporous Alumina Interposer for millimeter wave applications. So we've been developing this interposer for maybe 10 years now. It's an alumina interposer. It's a nanoporous alumina that we were able to grow nanowires in it. So we're able to interconnect the top and the bottom surfaces of the substrate. So we can do vias and do circuits with it, so crossovers, just interconnecting, feeding antennas from the bottom, different things we can do with it. We have done filters, we have done transmission lines, antennas, arrays of antennas, different types of structures on it. And now we want to start integrating active devices on this interposer. And aiming at the D band, we're looking at between 110 and 170 gigahertz to be able to integrate different active devices. We need to start worrying how to do it. So it's much more complicated than the microwave frequencies because the dimensions are electrically long. So we need to worry about the impedance. So when one of the possibilities is to do a flip chip. The flip chip, we get the chip and we flip it on top with copper pillars to reduce dimensions. But then we have two surfaces that can interact with each other and then can be really complicated to be able to integrate. Wire bonding, which is the classical solution, it's complicated as well because with wire bonding, the dimensions are big enough that you need to worry about the impedance. So if you look here, for small distances between the substrate, the effect of the substrate, of the height, the distance from the wire bonding, starts to get very complicated to do the impedance matching. So the idea here was to bury a chip and create a air bridge, but a CPW air bridge, to be able to control the impedance on this distance that's not negligible. So this is the beginning of our work. We showed it's possible to fabricate the air bridges, the air CPWs. We showed how to bury the chip on the interposer. We had some really good results of the air bridge itself, and then the next steps is to be able to connect here and here. We've been doing this right now. We weren't able to finish for the conference. We had really good losses, 0.2 dB per millimeter on the suspended bridge, which is really good. And now we're going to interconnect the dummy chip just to test interconnection, just to extract the behavior. And then we're going to substitute for different chips and amplifiers or LNAs, power amplifiers and LNAs, detectors, oscillators, different parts of active, so we can have a whole entire system. So that's our concept we're trying to show here. This is Professor Ariana. She works with me. She's part of our team here. She's been helping us develop this work for about 10 years now. So thank you very much.